Hi, we're back. This is April the 9th, 2015, and we're starting with part 4 of the Jolida amplifier repairs. So what we've got here, we ended up on our last one, we were kind of wondering about the transformer, the power transformer of this amplifier. So we set up a test. What we're looking at is the transformer current and voltage AC and the transformer current and voltage DC. These two meters are the DC readings, and these 2 meters are the AC readings. We have the stock diodes, 1N 5408s, and series capacitors, 470 microfarad, I think 450 volt. So this is a Jolida's stock setup, and what we're trying to do here is verify the transformer secondary output. We called Jolida. Jolida said the B+ voltage on this amplifier should be about 425 volts. And when we're pushing probably 40 watts output in making music, we're down, I don't know, 325. We also have the oscilloscope set up so we can look at the waveform. So let's get started here. Let's turn this thing on and see what happens. Alright, our loads are the light bulbs. We've got 3 60-watt bulbs in series. So here's the transformer AC side. We're we gotta reset this here. Okay, we're looking at 808.9 milliamps at 284 volts. There's a data plate on the transformer, and it says it's good for 300 milliamps, 300 volts. So obviously at 800 we're drawing a little bit more than 300, and our voltage has dipped to 284. Now that's AC volts, and that's AC milliamps. On the DC side, we're getting 345 volts at 488 milliamps. So those are the numbers. Looks like the transformer's doing pretty good. Looking at those numbers, it's putting out twice, a little bit more than twice of what it's supposed to be putting out, and we're still holding 284 volts on it. The signal from the transformer on the oscilloscope looks like this. We got 730 volts peak to peak, and our ripple is 12 volts. Now this is the AC input into the bridge, and then the DC output ripple of the bridge. So that's what that's looking like. So let me maybe put a smaller load on this thing so we can get that AC current down to about 300 milliamps, and at that point we should be holding 300 volts, which is what the data plate on the transformer states. And if that's the case, we've got a good transformer. So stand by. Okay, we're back. We've got 40 watt bulbs. We've got 3 40 watt bulbs tied in series, and this is what the numbers are. We've got on the AC side 291 volts RMS, and we're drawing 580 milliamps of current from the power transformer. Again, it's rated for 300 milliamps at 300 volts. So at 292, and drawing 580. We're looking pretty good there. On the DC side of it, on the DC side of the bridge, we've got 370 volts and 333 milliamps of current. So those are the numbers. Maybe if I went to a little bit smaller, we can get into the 300 milliamp range and find out what kind of signal we would be providing. Once again, here's the oscilloscope now. This is with the 40 watt bulbs, 3 40 watt bulbs. We got 760 volts peak to peak with a 9 volt ripple. So I'll see if we got some smaller light bulbs. I'll put a smaller load on it, and we'll see what happens. We'll be back. Okay, we're back. We found some 25 watt light bulbs. So there's 3 25 watt light bulbs, 75 watt total load. The transformer on the AC side is 300 volts at 400 milliamps. Once again, the rating on a transformer is 300 volts, 300 milliamps. So once again, we're looking pretty good there. Looks like the transformer is able to put out what it's what the data plate on it suggests. DC side, we've got 386 volts at 218 milliamps. So that's what the B plus voltage would look like with 215 milliamps drawn. I got a feeling that 4 EL34s, the plate circuit on that, is going to draw more than 218, but it is what it is. So those are what the numbers look like on all 4 meters. Once again, that's the transformer, AC, secondary power transformer for a Jolida amplifier, and then we have the bridge output. On the right hand side is milliamps and volts. Bridge output on the left hand side is the milliamps and volts of the transformer. The signal on the oscilloscope looks like 700, 800 volts peak to peak with a 6 volt ripple on this thing now, and that's with the loads that we showed over here. That's with a 387 DC voltage and 215 current draw. So there you have it. We'll be back. Okay, I also wanted to mention with these readings that we have here, we do have tubes installed in this amplifier. I had some older tubes. We plugged them in because we wanted that transformer also supplies the heater circuit for all the tubes, so we wanted to have that draw taking place on the transformer, and to get these readings we wanted to tax the transformer with everything it would see while it's operating. So once again, the tubes are installed. There's the stock bridge setup, stock capacitor setup, the way it comes from the factory, and then there's our output from the transformer, secondary, and the ripple voltage off the bridge. So that's where we're at right now. Hopefully we're going to come up with some kind of improvement on this thing and move it on down the road. Hopefully we can, according to Jolida, get that 425. I'll be happy with 400 volt on the B plus side. So we're working at it, and we'll get down there. Okay, we're back again. I wanted to do a recording on this thing, on the if there's any effect of these different diodes. We've tried 3 different style diodes. These are the least expensive. These are the 1N5408s. They range, these are 50 cents each, and then those Schocktys that we tried, those range, I think, $8 each. So at that price range, I wanted to see if there's a difference in performance on these things. So what we have here is the AC input to the bridge. We've got the DC output. This is the load, 325 watt, those small light bulbs. So they're 325 watt bulbs. And we're going to keep that the same, and we're going to try the 3 different diode configurations. Alright, so we're going to turn this on. Over here we got the oscilloscope so we can see what the signal looks like. So let's get it turned on. Alright, these are the 50-cent diodes with a 75 watt load. 790 volt peak to peak, 6 volt ripple. On the AC side, the output is 299 volts. This is from the secondary to transformer, and we're drawing 399 milliamps of current from the power transformer of the Jolida amplifier. On the DC side, we got 381 volts, and we're drawing 210 milliamps of current. So that's your 50-cent diode there. Everything else is the same. We've got the 2 caps in series with the small voltage divider to ensure both caps see the same voltage. So that's it. Those are the numbers there. We're going to go to one of the different diode sets there and see if there's a difference on this. So stand by. Okay, we're back. This is with the DGP diode. There's the breadboard. These are $1.23 each. On this we've got AC voltage 299, AC current is 392, so 392 milliamps and 299 volts AC off the Jolida power transformer, just by changing diodes. Same switch that down. Alright, same load. We got 383 volts DC and 216 milliamps of current. All we've done is change diodes. Same, everything else is the same. The voltage divider on this one, I think these are the 150s, 150,000 ohm voltage divider, whereas the other one might have been half that. But same capacitors, and I don't think the voltage divider should affect it that much, but those are the numbers there. AC, DC, and then the oscilloscope is showing us 780 volt peak to peak with a 6 volt ripple. So those numbers look pretty much what we had before. That's by basically going to 3 times the cost of the other diode. This diode is a 1500 amp reverse voltage diode, so looks like most of the meters are timing out. Get that back. So there you have it. We'll try that last configuration with the Schottky diodes, and we'll see what happens there. Okay, we're back. This is the 3rd configuration, or a 3rd set of diodes. These are the Schottky diodes. These are $8 each, so there's a big difference in price there. So let's see what they look like. On the AC side, we got 301 volts, 397 milliamps. So the current draw from the Jolida is 397 and it's putting out 301 volts. The spec on that transformer was 300 volts, 300 milliamps, so it's putting out more current and pretty much holding the voltage. On the DC side, this is with the same load. We got 75 watt load of 3 light bulbs, 25 each. We got 382 volts DC output, 216 milliamps. Voltage divider on this one I think is 62,000 ohms. So there's a slight variation on the voltage dividers for the capacitors. These caps are in series, so to keep each cap at the same potential, we've got that voltage divider network that provides that. So let's take a look at the oscilloscope on this. At 780 volt, peak to peak, 6 volt ripple. Not much has changed there. Alright, so that's the difference in from a 50-cent diode up to an $8 diode. So maybe on bridge rectifiers the extra cost might not be well spent. So there you have it. I thought this would be a good point to kind of do a little bit of a summary of where we're at. Basically, this amplifier, the gripe on it was that it was a little anemic in power output. So what we ended up doing was looking at the power supply board. And when looking at the power supply board, we saw that that channel A, the way it's clipped there, that is the output of the power transformer. So we saw that. Channel B right now is the ripple, DC ripple of the bridge rectifier output. So when we saw the flattening or the clipping of the transformer, we kind of wondered about that. We thought that perhaps the signal would decrease in amplitude, but not this clipping that we're seeing. So that basically led us to isolating the power transformer wires that are going into the power supply board and coming up with this breadboard circuit with different types of diodes that we've tried, and taking readings on the AC side. Right now you're looking at 1.1 amps of current and 260 volts AC. That power transformer is rated for 300. And on the DC side, the output of the bridge, we're looking at 314 volts DC and 770 milliamps of current. We got a pretty bright load down here. We got 3 100 watt bulbs. But we thought this would be a good point to kind of look at the schematics and also ask about this clipping that we're seeing here. Now that we get that with the capacitors connected, so we're going to disconnect the caps. These are filter caps that are in series on the output of the bridge. There's a voltage divider network. There's 2 resistors as a voltage divider, and they connect that across these caps to keep each cap at the same potential. So we're going to disconnect that, and we're going to see what effect it has on the signal. Okay, the capacitors have been disconnected, and we can see that just by disconnecting the capacitors, that's the only thing that's happened here. The signal looks more like a sine wave. Obviously the ripple is going off scale, so let's bring that down. Take a look at the ripple. Alright, that looks like a normal output from the bridge without any filtering done on it. 380 volt output of the bridge, and 770 volts. Now the only thing that was done here is the capacitors were disconnected. So that clipping or flattening of the power transformer has kind of led to all of this that we've done. So let's take a look at the circuit and where we're connected to, so you can have a better understanding what's going on here. This is the way everything is connected up. You can see the scope A channel are the pink markings, which is basically the output of the power transformer that feeds into the bridge. The blue markings are scope B channel. There's a current meter on the AC side, which is kind of greenish, and then there's a AC voltmeter, which is bright yellow on the AC side. On the DC side, you can see there's a darker yellow, which is the current meter, and an orange, which is the voltmeter. Now you can see the voltage divider there is on the output of the bridge, and there's two capacitors that are in series that are tied across the bridge output. So that's the circuit. We've got the light bulbs over there on the right, which is the load, and we've changed that around to different value bulbs to put different loads on this circuit and see what effect it has. So that's the circuit that we've been testing with. I'm going to show you what the actual amplifier circuit is. Okay, this is the actual amplifier schematic. Once again, there's that bridge, the power transformer, the two capacitors and two resistors. This is the power supply board, and it feeds up onto the amplifier board. You've got the B plus voltage, which is right there, and then you've got the two taps that are after that through a voltage divider network that drops the voltage. But according to Jolida, that B plus voltage should be around 425 volts. We're not seeing that. So that's led to all of this. Once again, there's the circuit. These are the numbers we're seeing right now. This is with the filter capacitors off. We're 246 volts DC at 641 milliamps. And on the AC side, we've got 10 volts AC, 720 milliamps. Must be something going on there. Over here we've got 770 volts peak to peak, and 380 volts on the DC side. That 770 is the output of the transformer, which should be shown over here in RMS, but for some reason it has been disconnected. We probably got that clip disconnected. Alright, anyhow, that's where we're at right now. We're going to probably come up with a plan B here and move this down the road. Okay, we wanted to get one more shot of this. We put the caps back in, and you can see how it flattens out the circuit. Also, it has a big effect on current from the transformer. So with the caps back in, transformer's drawing 1.1, almost 1.2 amps, and our voltage is 265 on the AC side. DC side 775 and 317. So those are the numbers. Once again, these are the Schottky Diodes. This is what was connected up to the load. So there you have it. Okay, we dropped the load to 21 watts total. We've got 3 7-watt lights, and what we wanted to do is see if this, being that we got within the current draw of the power transformer, it's rated for 300 volts at 300 milliamps. We wanted to see if that eliminated a clipping that we would see going into the bridge. So you can see here, this is the current draw on the power transformer. It's 138 milliamps at 309 volts. Once again, it's rated 300 milliamps, 300 volts. This is the DC side of the bridge. We're pulling 64 milliamps, 65 milliamps at 400 volts. The load is 3 7-watt bulbs. The bridge again, a bridge has these are Schottky Diodes, voltage divider, and then those are the capacitors that are in series. One thing we've changed here is the load. The oscilloscope still shows a clip. We got a 2-volt peak-to-peak ripple with a 820 volt output from the transformer, and then you can see that it's clipped. Now when we did this with the Variac, I don't know, we were 400 volts I think, but there was no clipping involved off that Variac power transformer. But here we are on the audio transformer, and for I'm sorry, on the power transformer for the amplifier, and we're seeing this clip. The clip is back. We don't really understand why that happens, but there it is. All right.